So today I'm going to be introducing you to a couple of forms of what we call simple harmonic motion. I'm going to introduce you to the two most common forms that we're going to see in AP Physics. Now this doesn't mean that these are the only forms that we're going to see, but they are the two most common ones that we use to introduce the idea to you. Now the idea of simple harmonic motion is this, that as you take an object that is in equilibrium, okay, and notice that my block right now is, the bottom of it is essentially at the equilibrium line. This is where equilibrium, meaning that the forces are balanced, right? At this point, the force is on my block. I've got the force of gravity pulling down on my block. And then I've got the force of the spring, which has exactly the same force pulling up on the block. And if those two forces are equal, then my object is in equilibrium. So at this point, those two forces are essentially equal. However, if I were to take my block and I were to pull it down below my equilibrium point, what's going to happen? Well, hopefully you're recognizing that the force of gravity stays the same. That's not affected. However, because my string has stretched out more, remember that the force of the spring is equal to kx. That was Hooke's law. So x is the displacement. So I've just increased the displacement of my spring from the equilibrium point. If that's the case, the force of the spring should now be greater. If the force of the spring is now greater, then when I release it, the upward force is greater than the downward force, and Newton's second law says that the sum of forces equals ma, and so therefore if the sum of the forces is upwards, then the object should accelerate upwards. And so I release, and sure enough, that's what happens. Now, something interesting happens. Once I pass that equilibrium point, right, you can tell that at some point it passes my equilibrium point, it's up above that. Once I pass the equilibrium point, then now the distance of x is less than what it was before. So if x is less, then when I do my F equals kx, when I do Hooke's law, the spring force is now going to be less than what it was when it was at equilibrium. At equilibrium, they were equal. But now that it's above that point, the x is less, the force of the spring is less, and so therefore the force of gravity will be larger. And so now it's going to be pulling down. It's going to be trying to restore it back to that equilibrium, right? And so it's going to slow down, and then eventually it's going to stop and then come back downwards again until, again, we pass the equilibrium and repeat the process over and over and over. Now, the fact that this process is repeating over and over and over is what we call periodic. The same thing is happening over and over and over again. This is a special situation, though, in which we have something called simple harmonic motion. Now, in simple harmonic motion, we always have what's called the restoring force. And the restoring force is proportional to, but opposite the direction of the displacement. So if I displace it downwards from that initial equilibrium, the further I pull it, the stronger the restoring force is, the stronger the force of the string is trying to pull it back to that equilibrium. The same thing happens when I pass the equilibrium and come back up this way, right? The further I get up, the less the force of the spring is, and so the stronger that restoring force is trying to pull it back down to that equilibrium point. So the idea, again, of simple harmonic motion is that your restoring force, the force trying to bring you, or combination of forces trying to bring you back to equilibrium, that restoring force should be proportional to, but opposite in direction of, your displacement from this center equilibrium point. All right. Now, an interesting thing with the simple harmonic motion is that we will have a constant period. And I want you to see that, right? If I mark when it gets to the bottom, mark, 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 right? You can tell that I was saying mark at approximately the same rate. We could time that. We could pull out a stopwatch. We could use a slow-mo camera if we wanted, whatever. We could time how long it takes for it to complete one cycle, to go from the bottom up and then back down again. That time is what we call the period. The period of an oscillating spring is more or less constant. Now, my question for you today is, what are some of the things that you think might affect the period, the amount of time that it takes to complete an oscillation, right? Notice I've got a mass here, I've got a spring, I pull it down a certain amount, right? What types of things do you think might affect the oscillation of the spring? Not its speed, but the actual period. Now, don't go look this up. I know the first thing some of you are going to do is, let's go look at ChatGPT. Or let's go Google it. No, no Googling, no ChatGPTing. I want you to think about it on your own. What are some things that might affect the period of my oscillations? All right, come up with 3 to 5 things. If you come up with 3 to 5 things, when you come in next class, then you're going to chat about with the rest of the class, and you guys are going to come up with, as a class, about 5 things that you think might affect this, and then you're going to test them. You're going to find out through experimental verification which ones really matter and which ones don't. All right? So I don't want to ruin the surprise for you. No spoilers. I want you to try to think of what you think might matter. Some of those things will matter, and some of those things will not. Okay? I'll give you a hint on this one. One of the things that I think about is my actual physical spring. What if I change it? What if I use a spring that has a different spring constant, right? It has a different stiffness. Would that matter? Would that affect the period of the spring? I feel like it should, right? I feel like if it's more stiff or less stiff, that might affect the time that it takes to complete an oscillation. Okay? So I want you to think about that. You can change materials, you can do whatever, but what might affect it? Okay? Recognize that we could do this horizontally. If I did it on like a horizontal track, like an air track or the tracks with the carts, you could have something with a spring that's oscillating back and forth side to side. Okay? For today's experiment, because it's a little bit easier to work with, I want you to just work vertically. All right? So we're not going to do anything like, well, let's swing the block or let's do it side. No, don't worry about that. Just for the simple vertical situation of a block oscillating on a spring, what are some of the things that might affect that period of oscillation? All right? Now, that having been said, I have a second thing I want you to look at today. Okay? We have a string that is going to help us have a pendulum. All right? So, we're going to tie this off so that we can see it. Again, the pendulum kind of has this equilibrium point. All right? So, we're going to do a double half hitch there. That's my Eagle Scout for you. Okay, so we got a double half hitch that's holding that on there. So now we're actually going to swing it as a pendulum. This is kind of an equilibrium point, right? At this point right now, it is an equilibrium, right? The force of the tension is equal to the force of gravity. Now, one thing to recognize, once I start swinging it, that's technically not an equilibrium point anymore, right? It's technically not an equilibrium because as it moves through there, it doesn't stay at that height. If it were to stay in a straight line at that height, then we could say that the forces are balanced. The fact that as it goes through that point, it starts swinging upwards actually means that at that point, the forces are not balanced, right? The tension, we've talked about this before in class, the tension has to be a little bit bigger than gravity, otherwise it wouldn't swing upwards, all right? Now, given that, you'll notice, hopefully, that as I swing, tick, 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 tick. You'll notice that every time it got over to the right side there, I said tick. And that period was approximately the same for every swing. Again, this is a good example of simple harmonic motion. Now, the proof of that is a little bit more challenging. We're not going to go through that today, but recognize that the further you pull it away, the further it is away from its center point, you're going to have tension pulling this way, and you're going to have gravity pulling that way. The combination of those is going to cause a restoration force pulling us back towards what was originally our equilibrium, right? The further you are away, the larger that restoring force is, because the more of your tension that's going to be pulling that way, gravity is going to be less balanced by the tension, right? Tension has a little bit of vertical here, but gravity has a lot more vertical in that direction. The closer you get, the more that your tension balances out gravity, and so the less that the actual restoring force is. So hopefully you can kind of see again that idea of a restoring force trying to get us back to the center. As soon as I cross that center point, the restoring force is now back in the opposite direction. So again, we've got a pendulum. The pendulum has more or less a constant period, which you could measure that period. You could measure several periods. Again, you don't want to measure too many, because there is a little bit of friction up here with the string and the rod, the ring that's holding it up. There might be a little bit of air resistance. So you could do, 2, 3, 4 cycles and divide by however many cycles you did. Try to get a constant period there. The question is, of course, what are the different things that we could do to our pendulum here that might affect the period of the pendulum. All right, so you can think about that. You can think about what, in the general sense, might affect the period of a pendulum. Okay, and again, try to come up with 3 or 4 different things. Okay, 3, 4, 5 different things that might affect the period. Now, one caveat here is we are assuming that our string is massless. We are focused on the mass at the end of the string. Sometimes we call that the bob of the pendulum. We are focused on this being the mass that's swinging back and forth. We're going to assume that the center of mass is the center of mass of the bob. Now, the only way that that can happen is if there is 0 mass here. If there is mass here, then the center of mass needs to shift a little bit towards the extra mass that we have here. We are going to assume that the string is more or less massless, which compared to my 500 gram mass, it is. But you do have to be careful with that if you try in your lab, if you try smaller masses and things like that. You want to make sure that you're using masses that are large enough that we can continue that assumption that the string is massless. All right. Now, other than that, think about what you can change here. What are some different variables that might affect the period of a pendulum? All right. Now, again, you're going to test this out in class. You're not going to have 45 minutes for each test. You're going to have to test 3 or 4 things for the pendulum. You're going to test 3 or 4 things for the spring. So you're going to have to work with your partners, work with your group. You're going to have a little bit larger group this time. You have to work with them, make sure that everybody shares data from your group so that in the end, you can come up with a conclusion of what really affects these periods. Not only what affects them, but what is the relationship? Is it a linear relationship, right? So you may say, for example, the spring constant affected the oscillation of the spring earlier. If that's the case, does doubling the spring constant double the period of the oscillation? Does it half the period of the oscillation? Does it quadruple it, right? Is it a quadratic relation? Is it inverse? So I want you to think about not only does it affect it, but what exactly is the relationship between those two objects? And I'll let you think about it. I'll let you figure it out, and we'll come back in a couple of classes and talk about it. Okay? That's it for tonight. Get started on that brainstorming. What affects those periods? We'll see you next time.